Welcome to this explainer. Today we're diving into the totally fascinating invisible infrastructure that keeps the internet from collapsing into complete digital gridlock. I mean, we send emails, we stream movies, and we browse the web every single day, right? But we completely take for granted the massive, hidden world of routing and switching that actually makes all of it possible.
Seriously, when you really think about it, it's nothing short of a miracle that billions of devices can communicate simultaneously without catastrophic data collisions just tearing the whole system apart. Well, today we're going to find out exactly how they pull it off.
So here's our roadmap for today. 1. The local neighborhood. 2. Enter the router. 3. Inside the IP packet. 4. OSPF, the network GPS. And finally, 5. Making router neighbors. Let's jump right in.
All right, part 1, the local neighborhood. Before your data can ever cross the globe, it's got to successfully make it out of your local network first.
To really wrap our heads around local networks, we kind of have to understand the enemy first, and that is collisions. Imagine being in a super crowded, chaotic room where literally everyone is shouting at the exact same time. Obviously, no one can understand anyone else. Well, this is exactly what network engineers call a collision domain. When multiple computers on the same physical wire try to send electrical impulses simultaneously, the voltages literally crash into each other. It absolutely destroys network bandwidth, and it basically means everyone has to stop, wait for a quiet moment, and try sending again. So to fix this chaos, networks evolved. We moved away from legacy hubs, which were essentially just giant electronic megaphones, to highly intelligent switches. A switch acts like a hyper-efficient neighborhood traffic director. It actually reads the unique hardware MAC address of every single connected computer, and then it uses specialized microchips to create private, dedicated communication lanes. So no more shouting, and, crucially, no more collisions. Moving on to part 2, enter the router. Switches are brilliant for local traffic, but what happens when your data actually needs to leave the neighborhood? Well, enter the router. If switches operate at layer 2 to handle the local stuff, routers are the specialized computers operating at layer 3, the network layer. A router's entire reason for existing is to connect completely different networks together and decide exactly where your data needs to go next to reach its final destination. So while a switch breaks up local traffic jams, a router is the one directing the heavy, global traffic. But here's the thing, these routers don't just run themselves. They require some pretty complex configuration. To set up these vital traffic hops, network admins have a couple of physical options. You can use a direct local connection via standard console port for that initial setup, but there's also this really cool industry secret, an absolute lifesaver called the auxiliary or AUX port. If the network goes completely down and you literally cannot reach the router over the internet, you can actually plug a traditional dial-up modem into that AUX port. You dial in remotely over an old-school phone line, and you fix the problem out of band. Pretty clever, right?
Okay, part 3, inside the IP packet. Once a router is actually configured, its main job is inspecting the shipping labels on every single piece of data.
And looking inside an IP packet, it's honestly incredible just how much information is crammed into such a tiny space. This isn't just a basic destination address. It's a super complex, intricate set of instructions that the router uses to figure out the absolute best handling for your data. You've got fields for the IP version, the total length of the packet, congestion notifications, and even fragmentation flags, just in case the packet is way too big for the network to handle and needs to be sliced into smaller pieces. Out of all those complex fields, routers really rely on 3 main components to get the job done. They look at the 32-bit source address to know where the data originated, and the 32-bit destination address to know exactly where it's headed. But there's also this brilliantly clever safety mechanism called time to live, or TTL. Think about it. What happens if a packet gets lost between 2 confused routers and just bounces back and forth forever? Eventually, that would literally crash the internet. So the TTL is just a number that decreases by 1 every single time it passes through a router. When that TTL hits 0, the router simply destroys the packet, instantly preventing any catastrophic infinite network loops.
That brings us to part 4, OSPF, the network GPS. With our shipping label attached and protected by that TTL, routers need a way to actually find the absolute fastest path to the destination. And that's where OSPF comes in. It stands for Open Shortest Path First. It's an open standard, dynamic link state routing protocol. Honestly, the easiest way to think about it is like a real-time GPS system for the internet.
Instead of just knowing about the very next intersection, an OSPF router uses a complex mathematical formula called the Dijkstra algorithm to build a complete, perfectly synchronized map of the entire network area. It's constantly recalculating the absolute best route for your data on the fly. But how does OSPF actually know which route is the best? Well, it uses a metric called cost. And this just perfectly illustrates the engineering behind the protocol. Cisco routers figure out the cost of a route by taking 100 megabits and simply dividing it by the interface's actual bandwidth. This means the faster the physical cable, the lower the mathematical cost. And just like when you're driving, OSPF always wants the route with the lowest possible cost. So a super fast link gets a highly desirable cost of 1, while an older, much slower link gets slapped with a penalty cost of 10. When you compare OSPF to older TAC like the RIP protocol, it's super clear why OSPF is the modern standard for large networks today. RIP is what's called a distance vector protocol. It calculates the best path just by counting how many router hops are in the way, totally ignoring whether those connections are blazing fast or painfully slow. Plus, RIP has a hard limit of 15 hops. OSPF, it has absolutely no hop limit. It factors in the actual bandwidth speed, and its convergence, which is how fast it adapts when a cable gets cut or a network goes down, is practically instantaneous compared to RIP.
All right, final section, part 5, making router neighbors. Because before OSPF can calculate all these costs, the routers first have to actually meet each other.
And two routers connecting for the very first time don't just automatically trust each other with their private network maps. They have to go through this strict 8-step progression to form what is known as a full adjacency. It honestly looks a lot like an intricate, slightly awkward blind date, ensuring they completely trust one another before sharing their sensitive databases. Let's walk through the state real quick. The meeting phase kicks off in the down state, which is basically complete silence. Then, one router sends an introductory hello packet, moving them into the init state. When the second router replies and actually includes the first router's ID in that message, they hit the two-way state. Mutual recognition achieved. Now, if they're on a shared network, they actually pause to hold an election to decide who will be the designated router and the backup. This is super important because it ensures just one leader is in charge of organizing all the updates rather than everyone shouting at once.
Once that leadership is settled and they're comfortable, they move into the data exchange phase. In the X-start state, they decide who's going to dictate the pace of the conversation. Then, in the exchange state, they send out database descriptor packets, which is basically like sharing the table of contents of their network maps. In the loading state, they request the specific, detailed info that they're missing. And finally, they reach the ultimate goal, the full state. Both routers now have a completely identical, perfectly synchronized topological map of the entire network area.
It is genuinely mind-blowing when you take a step back and think about all of this. Every single time you click a link or buffer a video, this insanely complex dance happens in milliseconds. You've got switches isolating collisions on a microscopic scale, routers decoding dense IP headers and checking TTL limits, and OSPF algorithms instantly running mathematical shortest paths based on actual bandwidth, all of this while constantly forming these trusted adjacencies with neighboring routers. It really leaves you wondering, right now, as you watch this explainer, exactly how many unseen, invisible routers tirelessly worked together, passing your data along link by link just to deliver this very stream to your screen. Keep learning and always keep wondering about that massive, invisible grid working silently all around you.